Homogeneous differential equations with constant coefficients are frequently encountered, and they have the form that we see here. And note, I'm going to begin by discussing what the solution will look like for a general nth order, but if you understand the idea there, you can certainly apply it to the second order case, which we will see very frequently, along with an occasional third or fourth order. Now, the defining characteristic that makes this constant coefficient is that each of these coefficients, the an minus 1, all the way through the a1, are simply just, in the a0, are simply just constants. And then what makes it homogeneous is we have this all equal to 0. There's no leftover term that is non-zero and does not involve y. Now, in order to solve this, we have a very nice method. We made the educated guess that the solution is going to have this form e to the rt. Once that guess is substituted into the differential equation, it will always reduce down to this nth degree polynomial, which we refer to as the auxiliary equation. Now, note, we can easily get this auxiliary equation purely by inspection. We just make the nth derivative become r to the nth power, all the way down to note that 0th derivative becomes r to the 0th power. And what we need to do to find the general solution is determine n linearly independent solutions. But recall, an nth degree polynomial will have n roots. And based upon those n roots, we somehow form our n linearly independent solutions. And these 3 bullets below outline that process. When there are some number of distinct roots, we simply take e to the r1t, e to the r2t, all the way through e to the rmt. Those would be m, whatever number of distinct roots we have, linearly independent solutions. If there is a root that's repeated some number of times, then the number of times it's repeated, we will need that many linearly independent solutions. So if it's repeated twice, e to the rt and te to the rt will be 2 linearly independent solutions. And that's the case we see most often. But note, for every repetition, we just keep adding to it a power of t. And then finally, when we have complex conjugate roots, we have these 2 corresponding linearly independent solutions. Let's go ahead and investigate a nice concrete example. So let's find the general solution of the given differential equation. And note, purely from a classification perspective, this is a third order. It is a homogeneous differential equation, and all of the coefficients are constants. So it's really kind of our ideal scenario. To solve, we simply write down the auxiliary equation, and recall the order of the derivative becomes the power of r, so that y term at the end becomes a 1. Then we go ahead and we factor. Now, if it's a quadratic, we can sometimes factor quickly. If not, we would use a quadratic formula. But when it's a higher degree, and for us in here that would typically be third, fourth order, we might need to use some type of polynomial division. But of course, in order to perform that polynomial division, you need to know a root of the polynomial. So we begin by making a list of what we consider possible roots. And in this case, it works out really well. We take any divisors of that constant term, which is just 1, so its divisors would be plus or minus 1, and then divide by any divisors of that leading coefficient, which would also just be plus or minus 1. So the only possible roots, if they're going to be rational numbers, would have to be plus or minus 1. And by inspection, I think we can see 1 is not a possibility because we have all positive coefficients, and if we substituted r equals 1, we would have 1 plus 3 plus 3 plus 1, which is most certainly not 0. So we can go ahead and cancel off that positive from the list. So the only potential rational root would have to be minus 1. So let's just use synthetic division and see if it works. So if our root is minus 1, and we're dividing into r cubed plus 3r squared plus 3r plus 1. So note these terms are going in descending order of the coefficients of the polynomial. Then we play our synthetic division game. The 1 comes down, and when we go back up diagonally here, we multiply by that potential root minus 1 up front. When we go downward, we add. Upward diagonally, we multiply by minus 1. And finally, at the end here, we do get 0. And this indicates to us that minus 1 is a root of the polynomial. So we have a factor, r plus 1. And to determine the coefficients of that remaining quadratic, we simply look at, kind of the bottom of our synthetic division to the right here. Those numbers 1, 2, and 1 respectively are going to be the coefficients for the r squared r and constant term of that quotient polynomial, the quadratic. So in this case, we would have r squared plus 2r plus 1. And this is really the ideal scenario. Once you get it reduced down to a quadratic, you know you can factor, or when you cannot, you use the quadratic formula. And in this case, it factors very nicely. That's just r plus 1 quantity squared. So we have a repeated root of r equals minus 1, and it is repeated 3 times. So our roots are minus 1, minus 1, and minus 1. So our general solution will have 3 terms. Our linearly independent solutions will be e to the minus t. For that next repetition, it will be t e to the minus t. And finally, for the third repetition, it would be t squared e to the minus t. 3 linearly independent solutions. So we combine these together appropriately with constants, and we have the general solution.